Okay.
All right, we should
I
begin.
think it's working.
So you might think that the best part about being a program chair is dealing with angry emails or conflicting PC personalities or trying desperately to stay on top of 450 plus discussions, but you'd be wrong. The best part is actually getting to help choose the best paper award winners. We had 3 such papers this year, and this is their session. We had 1 sort of unqualified best paper, and that'll be the first talk. And then we have 2 best paper awards for papers by early career researchers. So the first of our 3 best paper award winners today is Batch Arguments for NP from from Standard Bilinear Group Assumptions by Brent Waters and David Wu. And David will give the talk.
Great. Thanks a lot for the introduction, and thanks a lot everyone for coming. So today I'll be telling you about batch arguments, and this is joint work with Brent Waters. So in a batch argument for NP, a prover has a collection of M NP statements, and its goal is to convince the verifier that all M of these statements are indeed true. A natural way for the prover to do so is the prover can send over M NP witnesses, 1 for each statement, and have the verifier check that each statement witness pair is indeed valid. However, a natural question that we might ask now is, can we do better? Can we have the prover convince the verifier that all M statements are true with a proof whose size grows sublinearly in a number of instances? And then can the running time of the verifier similarly be sublinear in the number of instances that it needs to check? This is the setting of a batch argument for NP. The goal is to amortize the cost of NP verification. Namely, we seek a construction where the size of the proof grows with the size essentially of a single instance times something that grows polynomially in a security parameter, but more importantly, sublinearly and ideally polylogarithmically with the number of instances. We impose similar efficiency requirements on a verification time, where essentially the cost of NP verification for M instances should also grow sublinearly with the number of instances being checked. So batch arguments for NP is a special case of something called a succinct non-interactive argument, or a SNARK, for NP. However, if we look at existing constructions of SNARKs, they are either based on idealized models like the random oracle model or the algebraic group model, or they're constructed based on non-standard, strong, non-falsifiable knowledge assumptions, or they can be based on heavy cryptographic machinery like indistinguishability obfuscation. Here we see constructions from a single standard simple assumption. If we consider the relaxation of SNARKs for NP to the setting of batch arguments, then a series of works by Chodori, Jain, and Jin have recently showed how to construct batch arguments for general NP by leveraging the machinery of correlation intractable hash functions, which can in turn be instantiated either from the sub-exponential DDH assumption in conjunction with the QR assumption, or more recently from the plain learning with errors assumption. If we consider the setting of what's known in the setting of bilinear maps, we know how to construct batch arguments based on non-standard but falsifiable Q-type assumptions over bilinear groups. The focus of this talk is to give a new construction of non-interactive batch arguments for general NP that can be based on standard assumptions over bilinear maps. Namely, we can instantiate our construction using either the K-linear assumption in the prime order setting or the subgroup decision assumption in the composite order setting. But I think the more interesting and more salient point that I'm going to make here is that our construction is very low tech. It does not rely on heavy cryptographic tools like correlation intractable hash functions or on general information theoretic primitives like probabilistically checkable proofs. It takes a very direct algebraic approach for constructing batch arguments. In fact, it harkens back to a classic non-interactive zero-knowledge construction, or NIZI construction, by Grosso, Straussky, and Sahai that follows a familiar commit and prove paradigm. This is what I will show in a talk today. As a corollary of our main construction, we also obtain a RAM delegation scheme, otherwise known as a succinct argument, or SNARK, for P, with a sublinear size CRS from standard bilinear map assumptions. Previously, this was either known from, in the pairing-based setting, this was either known from non-standard pairing assumptions or required a long quadratic size CRS. As another corollary of our main construction, we obtain an aggregate signature that supports bounded aggregation from standard assumptions over bilinear maps. Previously, this was only known in a random oracle model. So now let me tell you a little bit about how we construct batch arguments for NP in our new framework. We follow a commit and prove strategy that's common in the construction of many other kinds of proof systems. Yet the setting is as follows. Suppose you have a prover, and a prover has a stack of M NP statements, and it wants to convince the verifier that all M of these statements are true. Here, we're going to work towards the NP-complete language of Boolean circuit satisfiability. And for simplicity of description, I'm going to assume that all of the gates are NAND gates. So we have a collection of M circuits. And so essentially what you can see is that for each of these wires, we actually have a vector of M wire labels, one wire assignment for each instance in my relation. So what the first thing the prover is going to do is the prover is going to construct a vector commitment to each of these wires in the Boolean circuit. Each of these vector commitments is a commitment to M wire assignments, M01 values. Importantly, for our construction, we will require that these vector commitments be succinct. Namely, the size of a commitment should scale polynomially in a security parameter, but importantly, polylogarithmically, or better yet, independent of the length of the vector or the number of instances that we are committing to. In our particular case, the length of the commitment will actually be independent of the number of instances. Now, once the prover has committed to all of these assignments, to all of the wire labels across all of the instances, now the prover has to reveal or convince the verifier that it actually committed to valid inputs. So this is going to consist of a sequence of validity checks. First, we have to check that the commitments to the input wires are actually consistent with the statements being proved. Here, this will actually be quite simple in our construction because the commitments will actually be deterministic. And so the verifier can simply compute for itself what those commitments are. Next, we have to check that each of these commitments to the wire labels are actually valid values. In the case where we are working with Boolean circuits, each of these wire values should be a 0-1 value. These should be Boolean value. So the wire validity checks will check that each of these commitments is to a binary valued vector. Next, we need to check that the wire values actually respect the gate constraints. Namely, for each gate in the Boolean circuit, the commitments to the output wires better be the NAND gate applied to the commitments to the input wires. And finally, we need to check that all of the output wires are indeed 1, namely that the circuit accepts on all of the inputs. So these are the 4 checks that we will describe in our construction. And the important observation that we will leverage in the construction is that each of these validity checks can essentially be encoded as a quadratic polynomial, and thus they can be checked in the exponent with the help of a pairing. That will be the underlying idea for our construction. So first, let me describe how the commitments operate. Here, we will simply use Pedersen multi-commitments. And for simplicity of exposition, what I'm going to describe in today's talk is our construction using composite order bilinear groups. So in particular, the group G will be a group of composite order. And for the first part of this talk, everything is going to work in a subgroup of order P. Later on, when I talk about the security analysis, we will actually use the full group. But for now, everything works in a subgroup of order P. So just to recall, in the Pedersen multi-commitment, if I want to commit to a vector of M things, the common reference string is just going to consist of M random group elements. Okay, and for ease of exposition, I'm going to write this at the exponents in bracket notation. So this will denote an encoding of this particular value in the exponent. So the CRS just consists of M random group elements denoted by these M random exponents. To commit to a particular vector, here a vector of wire assignments, we're simply going to take a subset product of these group elements. So if you look at the action of what's happening in the exponent, we're basically going to take a subset sum of these random exponents. So that will be the commitment to a vector. So what remains is to simply show how we argue that these committed values are actually correct or actually respect the circuit constraints. So here I'm going to describe how we validate that every single wire is a 0-1 value. That is actually a commitment to a Boolean labeling of every circuit in the instance across all of the instances. So we can encode this labeling function as a quadratic predicate, namely an input x is binary value if x squared is equal to x. So the key idea here is we're going to now use a pairing to check this pairing relation or this quadratic relation in the exponent. And just to recall what a pairing is, it's an efficiently computable bilinear map that essentially gives us the power to multiply exponents in a target group. This is the property that we will leverage in our construction. So what we're going to do is the following. We're going to take the commitments, so the subset sum of the exponents, and we're going to pair it with itself. And then we're going to also consider the pairing of the commitment with a commitment to the all ones vector, namely the sum of all of these exponents in the exponent. Okay, so these are the 2 quantities that we're going to study. So let's see why these two quantities are actually useful. Let's first expand the pairing of the commitment with itself. So when I pair the commitment with itself, the commitment is a subset sum of exponents. If I pair it with itself, I'm simply going to get this quantity squared. So I can write out, expand all of these components, and basically I can decompose the result into two sets of terms. One set of terms I will call the non-cross terms. These will be the case when I take the index I here and I multiply with the component in index I here. So the indices match, and I get something of the form alpha I squared times xi squared. And then I will have a bunch of cross terms, which is basically the products of an index I on one side and index j on the other for I not equal j. So it won't matter what these terms are eventually. What we'll focus on is just the non-cross terms. Okay, so this is the first equation that we're going to look at. The second equation is we'll pair the commitment with a commitment to the all ones vector. Let's see what happens here. Something very similar happens. Namely, here we have a sum of all the alpha i's. Here we have a sum of the alpha i's. We can again decompose this sum or this product into a collection of non-cross terms and then a collection of whatever's left, namely the cross terms. So here, let's just focus our attention on the non-cross terms. What is the relation that we're hoping to check? Well, we want to check that for each I, xi squared is equal to xi. That means that xi is a binary value. So if xi squared equals xi, observe that these two expressions are actually identical. So this means that if the prover did the correct thing, namely it constructed a commitment to a binary valued vector, these two equations, these two relations here would actually be identically valued modulo some differences in these cross terms. So how do we complete the check? We're simply going to give the prover the ability to eliminate the cross terms in the construction. So these two quantities will be equal, except it's some differences in cross terms. What is that difference? Well, it's this expression here that depends on alpha I, alpha j for I not equal j. So what we are going to do is we're now going to augment the common reference string with a collection of cross terms. We're just simply going to publish encodings of alpha I times alpha j. So this will be included now as part of the common reference string. And the prover, it can take the common reference string and compute exactly the quantity here. To verify, the verifier will take this element, pair it with the generator, and boom, it derives the cross term that is needed for the verification relation to check out. So this completes the description of the verification relation. Namely, we pair the commitment with itself, pair the commitment with the commitment to the all ones vector. These should be equal if the prover was honest, modulo some differences in cross terms. We'll publish the cross terms in the common reference string. So now the prover can provide exactly the terms needed for the cancellation to occur and satisfy this relation. So the non-cross terms here are going to enforce the check that xi squared equals xi. This is the check that every component is binary valued. And then we have the non-cross terms that basically correct for this pairing check relation. So we can actually use what I just described, the same general strategy to enforce the gate constraints. So here I'm just going to give a very high level sketch. So our goal is to now show that if the commitments to the output wires of each gate actually respects the gate constraint on the input values to each gate. So again, we can write this as a quadratic relation, namely the output value should be the NAND of the input values. That is exactly saying that the output value should be 1 minus the product of the inputs. This is a NAND gate operation. This is, again, a quadratic relation. We can use the exact same principle that I just described to check this in the exponent. So I'm not going to go into details here. I'll refer to the paper, but it's using exactly the same underlying mechanism. So this actually completes the description of the construction. So to construct a batch argument, all we do is the following. We take a look at each of these wires, compute a vector commitment to each of those wire labels. And then we just check that each wire and each gate are properly computed. So the size of the commitment is just a single group element. So the size depends only polynomially in a security parameter and does not depend on the number of instances or the length of the vectors. For each of these wire predicates and gate predicates, again, the proof is basically this sequence of cross terms that's needed for the cancellation. Again, one group element each. So the overall proof size only depends on the size of the circuit times something that depends on a security parameter, completely independent of the number of instances that we're checking. So the one thing that I have not described is whether this is sound, right? So hopefully I've convinced you that this is a complete construction. Namely, if you have a sequence of true statements, you can actually, the prover can manage to convince the verifier. But is this sound, right? Does this actually work? The soundness here will require some care. So if we come back to the original construction, the commit and prove strategy used to build non-interactive zero knowledge by Grosov-Strahovski and Sahai, they had a very similar type of strategy. So how did they argue soundness in their construction? In their setting, what they did was they relied on the ability to program the CRS in a way that it is possible to extract a witness from the commitment itself. And for a false statement, if we have a false empty statement, no witness exists. And so this is sufficient to argue soundness, in fact, statistical soundness of the construction. So can we try to mimic a similar type of proof strategy in our setting? So here, we are going to run into a bit of trouble. The commitments that we use here are succinct. Namely, we're committing to a very long vector using a single group element. And so we can't hope, at least not from some kind of non-knowledge assumption, to extract the entire witness from just a single short commitment. So we need to rely on a slightly different strategy. And here we use something called local extractability or somewhere extractability that has featured prominently in many similar works on constructing succinct arguments and batch arguments in recent years. So the idea here is as follows. We will define two different distributions for the common reference string. What I will call the normal mode, which is what I just described, just having the random group elements and then the cross terms. And then there will be a second mode, which we will call the extracting mode. And the extracting mode will have a special index I associated with it. And it will have the property that when you sample a CRS in the extracting mode, there will be a trapdoor that will allow you to take a valid proof and extract from it a witness, but not a witness to all of the instances. We can't hope to do that because we don't have enough information. It will allow us to extract a witness for just the ith instance. So if the proof verifies, I can find a witness wi such that for the ith instance, this is a valid witness. And moreover, we will require that the common reference string in these two modes are actually computationally indistinguishable. So this is very similar to notions like dual mode proof systems or somewhere statistically binding hash functions, very similar paradigm. And if we can show these two properties, this is sufficient to argue non-adaptive soundness of the resulting construction. So first, I need to tell you how we sample the CRS in these two different modes. So first, what I've written here is the normal mode for the common reference string, just a collection of random group elements. Nothing has changed so far. I omitted the cross term for simplicity. If I want to switch to extracting mode on a particular index, here denoted I star, what I'm going to do is I'm going to take my CRS, which has m random group elements, and I'm going to lift element I star from being in a subgroup to the full group. So far, everything I have described works in a subgroup of order P. What I'm going to do now, when I want to switch to extracting mode, is I'm going to take that subgroup component and lift it to the full group. That's the only thing I change in a common reference string. And I define the cross terms analogous. By the subgroup decision assumption, which basically says a random element in a subgroup is computationally indistinguishable from a random element in the full group of a composite order group, we can argue that these two CRS distributions are actually computationally indistinguishable. So how does this help? So the trapdoor in our construction will be a generator for the order Q subgroup. And the way that we're going to extract, so suppose I have a commitment that's computed with respect to this new CRS, where in position I star, I have now switched from an element of the subgroup to an element of the full group. The way that we can extract is simply by projecting into the order Q subgroup. I'm going to say that a commitment is a commitment to 0 if its projection or its component in the order Q subgroup is 0, and is a commitment to 1 if it's non-zero. So using a pairing, I can efficiently perform this procedure. So what remains to show is that this actually successfully extracts a witness for the chosen target. So I'll just demonstrate it for the case of the wire validity checks. So consider again the wire validity check that I described earlier on in this talk. I'm going to pair the commitments with itself, pair the commitment with the all ones vector, and then have this final component, which is the cross terms cancellation component. So let's study this equation in more detail. What components does the adversary control? Well, the adversary gets to choose the commitment. We don't know how the adversary comes up with the commitment. It cooks them up an arbitrary group element. That's the commitment. And it can also choose this arbitrary opening or arbitrary proof V for satisfying the wire validity checks. Those components are under the control of the adversary. What's not under the control of the adversary, however, is the generator GP. and this commitment to the all ones vector. These are determined completely by the common reference string, and we can assume that the common reference string was honestly generated. So these components are outside the control of the adversary. The second observation that we will require is that if this pairing relation holds, because we are operating over a composite order group, right, a group of order p times q, by the Chinese remainder theorem, if this holds mod n, it must in particular hold in the mod p subgroup and the order q subgroup. So this relation holds in order p and the order q subgroups, and we're going to consider what happens in the order q subgroup. So the final ingredient that we will need in our soundness analysis is that if we look at this expression here, this verification relation has 3 pairing products that is computing, or 3 pairing operations. The final component here, we're going to pair something in the order p subgroup and something that's controlled by the adversary. The point is that because we're pairing with the generator for the order p group, whatever the adversary does completely vanishes. It cannot affect what happens in the order q subgroup. So if we only analyze what happens with this verification relation in the order q subgroup, we have basically isolated a single instance, the instance I star. So let's just see mathematically how that happens. So let's suppose that the commitment is just some group element, has some component in the order p group and the order q group. Our adversary can choose this arbitrarily. The commitment to the all ones has a particular structure determined by the CRS. So if we consider this relation in the order q subgroup, whatever the adversary does here has no effect. We can just completely ignore it because it's projected away. All we're left with is the relationship here. So the relation that needs to be satisfied for this equation to hold is in the order q subgroup, whatever the adversary chose for the commitment, quantity squared, must equal whatever the adversary chose for the commitment times this honestly chosen value r. This equation has only 2 solutions. Either t is equal to 0, in which case this was a commitment to the bit 0, or t was equal to r, which in this case means that this was a commitment to the bit 1. So in this way, we have argued that if the wire validity checks pass, then in the order q group, the adversary could have either committed to 0 or committed to 1. It must have used the honest strategy in order to satisfy this relation. And now, by a very similar type of analysis, we can also show that the extracted bits must also satisfy each of these gate predicates. So by a very similar analysis, I won't have time to show the details here. So this completes the soundness analysis of our construction and actually gives a complete batch argument for general NP. So again, just to remind you how the construction works, the prover starts by committing to all of the wire assignments across all of the different instances, and then the prover gives a proof that each commitment to the wires are binary valued, and that all of them respect the gate constraints. So this is a commit and prove strategy for constructing batch arguments. So now let me just tell you about a few extensions to the basic construction here. So far, everything I've described is in your setting of composite order groups. Suppose you want to work in prime order groups. This is actually fairly standard to do. The way that we will do it is we will simulate these subgroups with subspaces in a vector space. And this projecting property we will implement using an outer product of vectors. So using this, we are able to construct an analog of this construction using prime order asymmetric groups, and we can base hardness on the standard k-linear assumption for any k that's at least 1. The second thing I want to tell you is that if we look at the construction that I've described so far, it has a very long CRS, right? The CRS consists of these random group elements, 1 for each instance, and it also consists of this giant collection of cross terms, right? We need to, right now, as I've written it, it's the size of the CRS scales quadratically with the number of instances. It turns out that we can improve upon this using a standard recursive composition strategy, very similar to the one previously used by Kalai, Pineth, and Yang. We can actually reduce the size of the CRS from quadratic in the number of instances to m to the epsilon for any constant epsilon. So you can choose epsilon however small you want. Of course, we're going to blow up by a large polynomial insecurity parameter, but the dependence on the number of instances can be an arbitrarily small polynomial in a number of instances. Finally, once we have a new batch argument for MP, we can use it to get a succinct argument or snark for P, or otherwise called a RAM delegation scheme. This essentially is just by plugging everything in to to the previous compiler by Chidori, Jin, and Jin. So just to recall, in their compiler, they show how to start from a batch argument for MP. In conjunction with a somewhere extractable commitment, this can be used to obtain a delegation scheme for RAM programs. Our work, we give a new construction of batch arguments for MP. And our techniques essentially also give us a somewhere extractable commitment. It doesn't follow as a black box, but using the same kinds of methodology, we're able to construct this also from standard pairing-based assumptions. And this combination is sufficient to get a delegation scheme for RAM programs, where the size of the common reference string scales polynomially or sublinearly with the running time of the computation being checked. So previously from pairings, this either relied on non-standard assumptions or needed a quadratic size CRS. Okay, so to wrap up, the focus of this talk has been on constructing batch arguments from standard assumptions over bilinear maps. And the key feature of our construction is that it gives a very direct construction, direct algebraic construction of batch arguments, and avoids the heavy cryptographic or information theoretic tools that have been commonly used in previous constructions. It gives a direct commit and prove approach for realizing batch arguments. And as the corollaries, we get a RAM delegation scheme, we get an aggregate signature scheme that supports bounded aggregation in a plane model. And with that, I'll conclude. Thank you very much.
So we actually have plenty of time for questions despite the late start. So for questions, encourage you to come down and use the microphones on the side. Maybe while people are waiting. I have a question, actually. Can you say a little something about the split verification procedure?
Yeah, so the split verification procedure basically says you want to split your verification procedure into an offline phase and an online phase. So normal verification, first of all, will require that the verifier read all of the statements, right? Because it needs to check that your proof is actually valid for a particular set of statements. And that will always grow linearly with the number of instances. So with split verification, what we want is there's two phases. There's an offline step and an online step. The offline step is allowed to depend on this full sequence of statements, and it outputs a very short verification state. And online verification then only needs to read a short verification state and can scale sublinearly with the number of instances. And that's actually critical for this recursive bootstrapping, because we want that the verification algorithm that we're going to compose with itself to actually have a verification size that is much smaller than the number of instances. So that's why we split it into a pre-computation step and a post-processing step.
Okay, thank you. Questions? Oh, we have some now. Yeah, here in the front.
Mm-hmm. Mm-hmm. So you want to get from quadratic to linear size CRS. Yeah, so then you only have to compose once. So I think it goes from lambda to something like lambda squared. Yeah, I would have to check the concrete thing. I think it basically blows it up by a quadratic factor. Mm-hmm. So that was just for I think, for the commitment to the all ones, right? So the commitment to the all ones vector, in this case, in the extracting mode, we had to move from the subgroup to the full group. So it was actually critical for the soundness analysis that at least one of the components in the CRS actually has a non-zero component in order Q subgroup. So that was needed for the extraction. So for the security proof. Yeah, so yes. So in order to invoke subgroup decision, it says that random element in the subgroup is indistinguishable from a random element in the full group. So you cannot have the random element in the full group have a 1 in the GQ subgroup. Mm-hmm.
Other questions? Yes, here.
Yes. Mm-hmm. That's right. That's right. That's right. So you have to be.
Can you repeat the question?
Oh, yeah. So the question is about adaptive soundness, and can we hope to prove that from standard assumptions? Yes. So yes and no. So I don't think there's any barrier to showing a batch argument with adaptive soundness. Now, if you have a batch argument of knowledge, so you can actually extract a full witness, and it's adaptively sound, that would actually be sufficient to get an adaptively sound snark, which, but then by the Gentry-Wicks separation, would mean that we would likely have to rely on some kind of non-falsifiable assumption. But at least if we don't require a full argument of knowledge, if you just want soundness, it is potentially plausible that we can have fully adaptive soundness. I don't think there's a separation currently, no.
Time for one more question. Yeah, here.
Yeah, pretty close. Moving time interact with DRS. I assume that before that, moving time is quadratic in the number of instances. How does that
Yeah, so basically, yeah, that's a great question. So how does the proving time interact with the sort of this recursive bootstrapping? So essentially what happens is then each time you recursively compose, it takes you from a CRS of size, let's say lambda, to square root of lambda. And the proving time and the blow up, sorry, it goes from square root of m to m to square root of m. And the blow up in the security parameter roughly goes from like lambda to lambda squared. So basically, I think you incur a factor that is quadratic in the security parameter. Yeah, so I think for concrete efficiency purposes, it's probably advantageous to actually just use the base construction and not use the recursive composition. So the recursive composition, I think, is just interesting from a theoretical feasibility perspective. But if you were to use the construction, I would recommend using the one with a quadratic size CRS.
All right, with that, let's thank David again.
Great, thank you. Great, there you are. Thank you.
All right, so the second paper in this best paper session and our first best paper winner by a early career researcher is Breaking Rainbow Takes a Weekend on a Laptop by Ward Bullens. And surprisingly, Ward will give the talk. So Ward, please.
Yeah. So hello, everyone. Yeah, I'm talking about cryptanalysis of Rainbow. So I'll start by explaining what is Rainbow. So it's one of the finalists in the NIST post-quantum competition for digital signatures. The other two being Crystal, Dilithium, and Falcon. They're based on structured lattices. And Rainbow is different. It's based on multivariate quadratic equations. Yeah, it has some good properties. Like the signatures are quite small, and it has good performance in terms of signing time and verification time. The drawbacks are that the public keys are quite large, and yeah, as it turns out, that it's not secure. So that's what we'll talk about today. Okay, so the history of Rainbow starts actually before a rainbow was invented. So it's based on this scheme by Patarin from 1997, where he invented the oil and vinegar scheme. But yeah, this scheme had the drawback that public keys are quite large. So in 2005, Ding and Schmidt invented this variant of Rainbow that somehow combines multiple layers of oil and vinegar to get something with slightly smaller public keys. And then there was a lot of cryptanalysis right after it was invented, but that dried up pretty quickly. And I think in 2008, the last attack was found. So and then there was a long period where nothing really happened until Rainbow was entered in the NIST process, and then people started to look at it again. There were some results about min rank attacks. So these are attacks that reduce a key recovery on Rainbow to the min rank problem, which is where you give some matrices, and the problem is to find a linear combination of them with low rank. And there has been some improvements in solving this problem. Actually, one of the talks tomorrow is about this line of work. And so yeah, but this is more of a it's not really a new attack. It's just like the existing reduction to min rank got more efficient as an attack. Also, there was some new analysis of the rainbow band separation attack that showed that the attack was slightly more powerful than we thought before. But yeah, all in all, there were no really new attacks on Rainbow until the third round. So it was selected as one of the finalists. But then things started to go wrong. So I had a paper at Eurocrypt last year where I gave like a different description of Rainbow. So the schemes are completely equivalent. It's just some different way of looking at it, which is, yeah, it avoids coordinates and changes of variables. So it's more elegant mathematically, and it allows you to see what's really going on. And this allowed me to find some new attacks. And yeah, those attacks only reduce the security level by 20 bits of security, which the Rainbow team claimed was they claimed to have enough margin to still meet their goals. But then in this work, I found a much more efficient attack that can actually break the security level 1 parameters in practice. Yeah, so yeah, this is a table with the estimated bit costs of the attack. So as you can see, the security level 1 parameters for the second round, the number of gates to do the attack is roughly 2 to the 61, which translates to 1 weekend on the laptop, which is where the title of the paper comes from. Right, but for the higher security levels, yeah, the cost is still quite big. So for example, 2 to the 131 for security level 1 of security level 3 of the second round, which is still out of reach of laptops and other computers that we have. Okay, so yeah, that was the introduction. So I'm first going to talk about this oil and vinegar scheme a little bit more, because you can't really understand Rainbow but without knowing how oil and vinegar works. Then I'll talk about Rainbow, then the attacks, and then I'll end. So I mentioned it's a multivariate crypto system. It's based on a multivariate trapdoor. So what's that? That's yeah, just a trapdoor function that is a multivariate quadratic function. So it's just a bunch of quadratic polynomials in some variables. Like this example is a map in 3 variables with 3 components, and this is what our trapdoor function is going to look like. So you can evaluate this function very easily. You just plug in your values and evaluate the function. And the idea is that this map looks random. And for random maps, we believe that finding pre-images is hard. But actually, there's some hidden structure. And if you know the structure, then you can sample pre-images for these maps efficiently. And then, yeah, once you have such trapdoors, you can just build signatures exactly like how RSA signatures work. So your public key is your trapdoor function. Your secret key is this trapdoor information. And to sign a message, you just hash to your output space. And then your signature is a pre-image for this hash. Right? So anyone can verify if your signature is correct. But in order to produce a signature, you need to know this trapdoor information. Right? So this is just exactly how RSA signatures work. But the question is, how do we produce these trapdoored multivariate maps? And yeah, this is there's multiple proposals, but the simplest one is this oil and vinegar trapdoor. So the trapdoor structure is very simple. So it's just a linear subspace O, and your trapdoor function is just a bunch of quadratic polynomials that vanish on this space O. Right? So for every vector in our space O, P of O is going to be 0. So that's it. So there's no extra information. To generate such a trapdoor function, you just first pick your space O uniformly at random, and then you pick your polynomials uniformly at random such that they vanish on O. Right. So this you can do. So the question is, how do you use this trapdoor information to actually sample pre-images? And before I explain that, I need to introduce this definition. So if you have our multivariate map P, we can define its differential at some point x. I call it d of x, and it's just defined as P of just P of x plus y minus P of x minus P of y. And yeah, you can verify very easily that this is a linear function. It's also linear in the point x, and this is going to be useful to understand how oil and vinegar works, but also for the attacks. All right. So now with this differential, how do you use the trapdoor? So we're given our trapdoor space O and some output value y, and we want to find an x so that P of x is equal to y. And the idea is very simple. You just first pick some uniformly random input v. P is not going to be a solution, of course, but you can solve for some correction term in O, such that P of v plus O is going to be whatever you want it to be. And it turns out that doing this is just a system of linear equations, right? Because with our definition of the differential, we can write P of v plus O as P of v plus P of O plus this differential, right? If we go back to look at this definition, you just move the P of x and P of y to the other side. And now the trick is, because P vanishes on O, we can ignore this middle term, and what remains is just P of v, which is some constant, and then some linear function of your O. Right. So this is just a linear system of m equations, right? Because our P has m components, and we have m degrees of freedom, namely O can be in this space O, which has dimension m. So with large probability, this will have a solution, and then you just output as a signature, or as your pre-image P, you output V plus O, right? And it can happen that your system does not have a solution, but then you just try again with a different V, right? So this is how oil and vinegar works. It's, I believe, a very elegant scheme. It's just the only structure is this subspace O on which P vanishes. So yeah, that's quite nice. And now how does rainbow work? So it's a bit more complicated. Instead of one space O, we now have two spaces, so O1 and O2, and they sit inside of each other. And there's also a space W in our output space. And the map P now behaves nicely on these subspaces. So there's three properties, namely it sends O1 to W, it vanishes on O2, and then there's another property involving this differential. Namely, for every point X, we want that the differential at X sends O2 to W. Right, this might seem a bit random for now, but yeah, this is what you need to sample pre-images. I'm not going to explain in detail how it works, but basically you use the oil and vinegar ID first to sample a pre-image that is correct up to a vector in W, and then you use the oil and vinegar ID again with O2 to get a pre-image that is correct exactly. Yeah, but that's not too important for us right now. So yeah, now I'll talk about the attacks. So yeah, we're going to use this property that I mentioned before about the differential. So I'll repeat. So for every vector X, if you look at the differential at X, this is a linear map that sends our O2 space, which is one of our spaces in the secret key, to W, which is another space in the secret key. So yeah, we have a lot of these maps, right? For every X, we have a linear map that behaves on these two subspaces, and our goal as an attacker is to find O2. So the way I solve this problem in my Eurocrypt paper was to reduce this to a min-rank problem. But actually, there's a much easier way to use these differentials. And that is the observation is that these differentials are much more likely to have kernel vectors in O2. So why is that? You can just compute the average number of non-zero kernel vectors in O2 of these differentials. And it's this quantity over there. So the size of O2 minus 1 over the size of W. So yeah, why is this? So there's O2 minus 1 non-zero vectors in O2. And each of them has a probability of 1 over the size of W of being in the kernel, right? Because its image under the differential is just a uniformly random vector in W. So with probability 1 over the size of W will be 0, right? And the dimension of O2 and W are the same. So this average number of non-zero kernel vectors is going to be very, very close to 1. And yeah, this is useful to us because we want to find these vectors in O2. And yeah, now a good place to look for them is in the kernels of these differentials. So yeah, I said the average number of those vectors is 1, but they come in clusters of size q minus 1, because every time you have 1 kernel vectors, then all the multiples will also be in the kernel. So heuristically, the probability of getting a non-zero vector in the kernel of the differential is close to 1 over q minus 1. You can have a precise formula, but it doesn't really matter. It's close to this. So yeah, with this observation, the attack is quite straightforward. So what we're going to do is we just guess a random x, and then we hope that the kernel of our differential intersects with our space O2 that we want to find. And then, yeah, we try to find a vector in this intersection if it exists, just by solving this system. So we're looking for an O such that d of x of O is equal to 0. Namely, it's the O sits in the kernel. And secondly, we want that P of O is equal to 0, just because P vanishes on O2. So that's how we can look for the O2. And yeah, so this is nice because the first equations, the d of x is equal to 0, those are just linear equations, right? So you can use those linear equations to eliminate variables from the quadratic equations. P of O is equal to 0. And this makes the system much smaller and easier to solve. So you can just use existing techniques to solve these systems. And yeah, if you use some implementation of the Wiedemann Excel algorithm, then it takes only 3.5 hours for each attempt of solving these systems. And on average, you need to repeat q minus 1 times, and q is equal to 16. So you need to repeat 15 times, which gives an expected runtime of 53 hours, or roughly 1 weekend. If you count Friday evenings as part of the weekend, then it's 1 weekend. So yeah, this is how you find 1 vector in O2. And it turns out that once you know 1 vector in O2, then you can recover all the secret key information very efficiently. So yeah, how does this work? Yeah, first we have this property of the differential. So for every x, we know that d of x of O will be in W. So since we know already a vector in O2, this gives us many vectors in W. So this immediately gives you all of W for free. Then once you know W, you can just solve for all the vectors in O2 that map into W under these differentials, and then you just solve a linear system of equations to find a basis for O2. So the only thing we still have to find is O1. And the way you do that is you take a quotient by O2 on the left-hand side and by W on the right-hand side. And actually, it takes a little exercise to prove that this quotient is well-defined, or at least that your map P is still well-defined on the quotient. But that's true because if you add some vector in O2 to your input, your output will change by some vector in W. That's exactly this condition on the differentials. So that means that our quadratic map is still well defined on these quotients. And then what's left is exactly an oil and vinegar public key, right? We have some space and some polynomials on them. There's a space on which they vanish, and you want to find this space. We want to find the quotient of O1 by O2. So we can just use existing attacks on the oil and vinegar scheme. And we can do this because now this is a very small oil and vinegar public key, because we quotiented out by two large spaces. So yeah, you can just use off-the-shelf attacks against oil and vinegar to find O1, and then you're done. And then we know the entire secret key. Okay, so that's it. So conclusions are Rainbow is not secure, at least the security level 1 parameters you can break in practice. It is possible to save the scheme by moving to larger parameters, but that would be quite expensive. Like the public key would be 4.4 times larger. The signatures would be 2.5 times larger, and the scheme would be 5 times slower. And it doesn't really make sense to do this because Rainbow was like a more complicated version of oil and vinegar that was trying to be more efficient. But now with these attacks, you're no longer more efficient than oil and vinegar. So we should really just move back to the oil and vinegar scheme, which is much more elegant and older and much better understood. So yeah, in my view, Rainbow is really dead. We shouldn't try to revive it and make it more complicated to save it again. We should just move back to this very nice and elegant oil and vinegar scheme and try to understand that one better. So yeah, that's it. Thank you.
Do we have any questions? No questions? Nobody wants to hear about the follow-up paper, what breaking Rainbow takes an hour on a BlackBerry or something?
Well, as I mentioned, I think we should stop caring about Rainbow. So if somebody wants to write that paper, go ahead, but that's not going to be me.
All right, in that case, let's thank Ward again. Okay. So our final paper of this best paper session is some easy instances of ideal SVP and implications on the partial Vandermonde knapsack problem by Catherine Bodgot, Arel Gacon, and Alice Pellet-Marie. And Catherine will give the talk.
Yes. Okay. Thank you for the introduction. And I'm very honored to receive this award together with my co-authors, as already said, Arel Gacon and Alice Pellet-Marie, both from the University of Bordeaux. So I got inspired by my own little teaser video that I made for the conference, and I will try to give the context and a summary of the contributions in form of an analogy. So using a mathematical problem as a hardness assumption in cryptography is a little bit like walking on a frozen lake and hoping that the ice is thick enough. And so the shortest vector problem is a mathematical problem on Euclidean lattices. And we are we are quite confident that the ice is quite thick here. However, if you restrict the problem to so-called ideal lattices, then past works have already shown that the ice has places where it's not thick, but actually you have puddles. And whereas the two puddles on the left and the bottom are very well signed, and you know how to verify if an instance falls into the puddle or not, the situation is a bit less clear with the puddle on the top right. And this deals with ideals that have additional symmetries. And so the picture of our first contribution is that we enlarge the puddle. So we make it a little bit bigger. But I think more importantly, we put a big warning sign around the puddle so that now you can easily verify if a given instance falls in it or not. And so now you can walk safely on the frozen lake again. And the second part of our paper deals with the so-called Pasha-Vandermonde knapsack problem. And without telling you now what it is exactly, you just believe me that it defines an ideal lattice problem. And we have to put this knapsack somewhere on the lake. And depending on what instance you have, it might be on different places on the lake. And now comes the second part of our, the result is that we show that there are specific instances of the Pasha-Vandermonde knapsack problem, such that the knapsack exactly falls into this larger puddle that we've shown. And we not only show this theoretically, but we actually implement the algorithm and run experiments on it. And so with this image in mind, I will try to lead you through this mathematical result. So I will first explain what exactly are those easy instances. Then I will show how we can apply this to the Pasha-Vandermonde knapsack problem. And then I will conclude where I clarify a little bit the implications of this result for lattice-based cryptography. Okay, so let's introduce the main mathematical object of this work, an Euclidean lattice. So an Euclidean lattice of rank n is usually described by a basis, and then the lattice is composed of all the linear integer combinations of those basis vectors. So I have a little picture in dimension 2, you see all the blue dots, that's a lattice. And then we associate to a lattice a minimum, which is the shortest norm of any of its non-zero vectors. And I think here you can see in orange, those 4 vectors are shortest vectors. And then the mathematical problem we are looking at is the shortest vector problem, where we ask for an approximation factor gamma to find a vector such that the norm is at most a gamma factor away from the minimum. So if we have, for instance, this violet circle here, then we have 4 more points that now are short and would be a valid solution to this problem. And now the main conjecture upon which lattice-based cryptography is built upon is that there's no polynomial time algorithm that solves the shortest vector problem, neither on classical nor quantum computers for polynomial approximation factors. And so in this work, we are looking at lattices that have an additional structure that comes from algebraic number theory. So I have to introduce a little bit the notions. So we have a number field K, which is of degree D, and OK, it's this ring of integers. And to every number field, we can associate a canonical embedding sigma that takes a field element and maps it to the real space of dimension D. So yeah. And then what we can do is we take a structure in algebraic number theory, as for instance, a module of rank R, and then map it via this canonical embedding to the reals. And now we end up in a lattice of dimension in the space of dimension D times R, where D is the field degree and R the module rank. But now this lattice inherits the module structure, and this is what we call a module lattice. And then we can do this, of course, that's just notation. So if the rank is 1, then we call this actually an ideal. And that's why we end up in ideal lattices. And then if I say module shortest vector problem or ideal shortest vector problem, I'm just talking about the shortest vector problem I've introduced before, restricted to module or ideal lattices. And why are people actually looking at this quite special variant of this problem? Because it's used as a hardness assumption for practical lattice-based cryptography. And so the main question that has occupied the community in the last 10 years or so is whether the shortest vector problem becomes easier once you restrict it to those special modular ideal lattices. And today I'm focusing on the ideal case and for very specific ideals. And so what's the state of the art of polynomial solvers for the ideal shortest vector problem on specific ideals? So those are exactly the puddles that I had in the picture of the introduction. So the first 2 works I would like to mention are here, the Kramer and co-authors paper that solves the shortest vector problem for principal ideals if the generator is Gaussian. And a second work, so that was the second puddle, is another work of Kramer and co-authors that now solves it for all ideals, but only if the approximation factor is super large, so sub-exponential. And so our work is builds upon those 2 works. That was the third puddle. And so the first one is due to Pan and co-authors, and they show an efficient solver for prime ideals that have additional symmetries. I will explain later what I mean with symmetries, where the approximation factor is quite decent with square root of the field degree. And then later, Porter and co-authors improved upon this by now applying this to all ideal lattices with symmetries. But now the approximation factor is much harder to grasp. And in particular, need the prime decomposition of the ideal and its norm in order to calculate this. And it's not very easy. And so our work now generalized these results in several aspects. So first, we are over all number fields. And then the set of our that we cover, so that is what I meant that we enlarge the puddle, is that so if we restrict the set of the previous work to polynomial approximation factor, then our set is strictly larger. And in particular, the partial Vandermonde knapsack problem that we will look at later falls into only this larger set. Okay, and then approximation factors are quite decent. And and that's what I said with the warning sign. So membership in our set can be very easily checked. And I have a little star at the all because it's actually not all ideal lattice, but only those whose prime factors are not ramified, but those are all but finitely many. Okay, so now I will, there's a bit of math coming now. I will try to explain what I mean with symmetries. So we have the number field of degree D, and we look at the group of automorphisms. And then what we define is this number Ni, that is the number of all the automorphisms that fix the ideal as a set. So we know that in this group, there's the identity, and the identity always fixes the ideal. So we know that this number is at least 1. But this group has at most D, which is the field degree, elements. So we know that this number is also at most D. And now comes this main theory from our paper, where we show that if we have an ideal whose prime factors are not ramified, then we have a classical algorithm that solves the shortest vector problem on this ideal in time roughly exponential D, the field degree, over Ni times log gamma, where gamma is the approximation factor. So if this Ni is 1, so the ideal is only fixed by the identity, then we recover an exponential time algorithm. This is what we have for general lattices as well. But if this Ni is a fraction of D, let's say D over 2, then we recover a polynomial algorithm as here the Ni cancels out the D. And this is exactly what I mean when I say that the lattice has many symmetries. And now, of course, it's relevant that it's easy to compute this Ni once you have a description of the ideal, like a basis, and a description of the group of automorphisms. and I think that's the last technical slide regarding the first contribution, is that now I want to give a little bit of an intuition why many symmetries help to solve the shortest vector problem more easily. So the Ni number that I just gave you is actually the size of the decomposition group. So that's just the same definition as what I gave you. And we can look at its fixed field, what we also call the decomposition field, so Ki. And then the main technical lemma in our paper is that if you're given an ideal, then you can intersect it with this fixed field, the decomposition field, and multiply it again with the ring of integers to recover your original ideal. And intuitively, what that means is that if you have a short vector in I, then it is also contained in this smaller set I intersected with this fixed field. And what this means is that the larger your HI, so the larger the number Ni, so the more automorphisms fix this field, this ideal, sorry, then the smaller becomes the fixed field because that's an inverse relation. And then the smaller becomes this intersection and the easier it is to find short vectors. So we can go down to a much smaller set and then lift it up by multiplying it with this ring of integers. So that's really that's the technical part of this contribution. Okay, then let's move on the partial Vandermonde knapsack problem. I guess that most of you have never heard of it, so let me introduce it. So we stay in our algebraic setting. So we have the number field of degree D. And now we look at some prime integer Q such that we know that the ideal generated by this number completely splits in prime ideals of norm Q. So we have D prime ideals. And now what we do is we select a subset omega of those D prime ideals and just look at the product of those prime ideals. Okay, and now the partial Vandermonde knapsack problem takes as a parameter a distribution over this ring that only samples element of short norm. And then the problem statement is that if we sample an element from this distribution and compute the coset E mod this special ideal given by those factors, then the problem asks to find and recover this E from the support of psi. So usually we take the parameter such that there's only a unique solution. And I didn't really specify how we choose this omega. And this is also because in the literature, there are two ways of doing it. So in the original proposal by Hofstein and co-authors, they did not specify how to choose the omega, besides some constraint on how large it should be. And in particular, they kind of suggested you can fix it. And in subsequent works by Lu and co-authors and another one I co-authored, we actually decided to add more entropy and to select this omega uniformly at random. Okay, so now I promised you that this partial Vandermonde knapsack problem lies on this frozen lake of the shortest vector problem. But it's actually not defining a shortest vector problem, but a related problem that is called a bounded distance decoding problem. So I have to introduce that over ideals. So we are given an ideal, and I give you what we call a target vector. And we are promised that it can be described as the sum of a vector that lies in the lattice and some offset E, where we are promised that this offset E is of small norm. So we know that we have a target vector that is somehow close to my lattice. And now this bounded distance decoding problem asks to recover either the offset or the lattice vector. That is actually equivalent. And now if we assume that our psi distribution from the partial Vandermonde knapsack instance is delta bounded, then having a vector that is the offset E mod this special ideal is exactly the same as writing it like a sum of a lattice point and an offset that is bounded by delta. So it's really like just rewriting partial Vandermonde knapsack gives you a bounded distance decoding problem. And of course, now the missing puzzle piece is that you have to map this bounded distance decoding instance to a shortest vector instance. And here I will be a bit hand waving because it's actually very standard technique and not so relevant for this talk. The really only important thing is that we map an ideal I to some related ideal I prime, and that those have a relation in the sense that whenever I has symmetries, then I prime has also symmetries and vice versa. So this reduction preserves symmetry somehow. And now we can think about how we can attack the Partial-Vandermonde knapsack problem. So whenever we can solve the shortest vector problem defined by this special ideal, then we can solve the Partial-Vandermonde knapsack problem. And it all, like with all what I've said in the first part, it comes down to when does this ideal has many symmetries. And now I will convince you by doing it from the other way. I will actually construct specific ideals for like this of this shape that are fixed by many automorphisms. So we know they have many symmetries. And I think that's the last math equations for this talk, is that, so what we do is we take the ideal generated by Q and fix one of the prime ideals, P, just call it P. And then we take a subgroup of the group of automorphisms H. And what you need to know, and I think this is like algebra 2 or 1, I don't know, math course, is that the automorphisms act transitively on those prime ideal factors. So if you apply this automorphisms on P, you will end up with one of those factors. You will always stay within the set. So of course, if you take a subgroup here, then this actually defines an index set because you're permuting within those prime ideal factors. And so if we define this ideal I omega H with respect to this subgroup, then we actually have an ideal that is fixed by this subgroup by construction. And for example, if you take a power of 2 cyclotomic of degree D, then we can have subgroups of order D over 2. So this is a fraction of the very large subgroups. And yeah, so we implemented this algorithm and run experiments on 2 different scenarios. So the first scenario is what I call a worst case omega. So this is when the adversary can actually choose the omega on their own for them advantageous way. And of course, they will choose the omega such that it's fixed by many automorphisms. And in this case, when we take parameter sets from the literature, we can solve Partial-Vandermonde knapsack in a very short amount of time. In the second scenario, where the omega is sampled uniformly at random, we cannot do this because with a very high probability, the omega will not be fixed by any non-trivial automorphism. So there will be no symmetries. But what we can do in the distinguishing attack is that we can forget some of the prime ideals, so forget some of the indexes in the set omega, then actually the problem becomes a harder problem, but we can hope for finding at least one symmetry. And this is what happens with a non-negligible probability. And then in this case, when we take concrete parameter sets, then we can reduce the 128-bit security claimed in one of the literature to 87. So it's quite significant. And I think that was the last slide, and I move on now to clarifying what are the implications to lattice-based cryptography. So the first thing you might wonder is if it's still a wise thing to use the ideal shortest vector problem to build cryptography. And I think it's a complex question, but we try to give guidelines. If you wish to do so, what we suggested you should follow. And so the first thing we suggest is that you check if you can increase your rank from 1 to 2. So that means that you're actually not relying on ideal lattices, but on module lattices where we have no weaknesses known, so no puddles in the frozen lake. If you can't do that, then we suggest that you use that you select your ideal randomly from a distribution where we know that this distribution is supported by what we call worst case to average case reduction. That means that this distribution gives you an ideal lattice that is as hard as possible. If you can't do that, then at least avoid bad ideals. So one class of bad ideals are the principal ideals with a Gaussian generator, as in previous work, or the ideals that we worked on in this paper that are fixed by non-trivial automorphisms. And in all cases, you should not rely on the hardness if the approximation factor is too large. then of course the question is what are the implications of our results on cryptography that is based on the partial Vandermonde knapsack problem? I haven't really talked about it, but there is a signature scheme and an encryption scheme and also an aggregate signature scheme. And when we apply our so our algorithm actually leads to quite severe key recovery and forgery attacks, but only if the omega is this specific, like very specific design choices. If the omega is random, then we can also only do those distinguishing attacks that halve the lattice dimension of the attack. And of course, this can easily be mitigated by increasing the parameters. And last but not least, what are the implications for lattice-based cryptography in general? I already said it, but I want to stress it again. Those attacks are only for very specific instances of the ideal shortest vector problem. And having many symmetries seems a very strong requirement and very unnatural for ideal lattice to have. And so there are no implications to the hardness of structured problems like the ring shortest integer solution or ring learning with errors problem, because actually they're based on the worst case hardness of ideal shortest vector problem. So you would, so they assume the hardness of the hardest instance and not on specific instances. And even if you would have, so those reductions actually only in one direction, even if you would have a solver, even if the lake would completely melt for ideal shortest vector problem, then we don't know how to use this to actually solve, for instance, the ring learning with errors problem. And even though I did not even talk about it, just to make it clear, so this work has absolutely no implications on the module learning with errors problem, which is the underlying hardness assumption of NIST candidates like dilithium and kyber. And I think this concludes my talk. Thank you for listening.
Do we have any questions? No? I think everyone's hungry. So let's thank the speaker again and head to lunch.